Part 1. Introduction and Historical Discovery. In the vast cosmic theater of our universe, few mysteries loom as large as dark energy. This enigmatic force, which comprises approximately 68% of the universe's total energy content, represents one of the most profound puzzles in modern physics. Like an invisible hand stretching the cosmic fabric, dark energy works in opposition to gravity, driving the accelerating expansion of our universe. The story of dark energy's discovery reads like a scientific detective novel, complete with unexpected twists and revolutionary implications. In the 1990s, two independent teams of astronomers set out to measure the universe's expansion rate, fully expecting to find it slowing down due to gravity's pull. The Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, embarked on what they thought would be a straightforward measurement of cosmy. Their tool of choice was Type 1a supernovae, extraordinary cosmic explosions that serve as standard candles in astronomical measurements. These supernovae occur when white dwarf stars in binary systems accumulate enough matter from their companion stars to trigger a thermonuclear explosion. The remarkable consistency of their peak brightness makes them ideal cosmic distance markers. As both teams gathered data throughout the 1990s, a startling pattern emerged. The supernovae they observed in distant galaxies appeared dimmer than expected. Not just slightly, but significantly so. After rigorous analysis and cross-checking, both teams reached the same shocking conclusion. The universe's expansion wasn't slowing down at all. Instead, it was accelerating. This discovery, announced in 1998, shook the foundations of cosmology. The teams had uncovered evidence for a mysterious repulsive force pervading all of space. A force that grows stronger as the universe expands. This force would come to be known as dark energy, a term coined by cosmologist Michael Turner. The significance of this discovery cannot be overstated. In 2011, Perlmutter, Schmidt, and Rees were awarded the Nobel Prize in Physics for their groundbreaking work. Their finding didn't just add a new component to our cosmic inventory. It fundamentally altered our understanding of the universe's past, present, and future. The historical context of dark energy extends beyond its 1998 discovery. In 1917, Albert Einstein had introduced a cosmological constant into his equations of general relativity, a mathematical term that could counteract gravity's pull and yield a static universe, which was the prevailing view at the time. When Edwin Hubble later demonstrated that the universe was expanding, Einstein famously called the cosmological constant his biggest blunder. Ironically, the discovery of dark energy has led to a resurrection of Einstein's cosmological constant, though in a modified form. Modern theories often interpret dark energy as a form of vacuum energy, a fundamental property of space itself, similar to Einstein's original concept, but with crucial differences in its physical interpretation. The discovery also brought attention to earlier theoretical work. In the 1980s, Soviet physicists had proposed the existence of vacuum energy as a potential driver of cosmic inflation, a period of rapid expansion in the universe's earliest moments. The connection between this early inflation and the current acceleration remains an active area of research. The revelation of dark energy's existence has spawned numerous research programs, theoretical frameworks, and technological innovations aimed at understanding its nature. It has also highlighted the limitations of our current physical theories and the vast gaps in our understanding of the cosmos. Part 2. Observational evidence for dark energy. The evidence for dark energy comes from multiple independent lines of observation, creating a compelling web of data that supports its existence. These observations, spanning different scales and utilizing various astronomical techniques, have transformed dark energy from a theoretical curiosity into a cornerstone of modern cosmology. Supernova observations, the primary evidence. The most direct evidence for dark energy comes from Type 1a supernovae observations. These cosmic explosions serve as reliable distance indicators due to their consistent intrinsic brightness. By comparing the observed brightness of distant supernovae with their expected brightness, astronomers can measure how space has expanded throughout cosmic history. The key finding from supernova observations is that distant supernovae appear about 25% dimmer than they should in a universe where gravity is the only significant force affecting cosmic expansion. This unexpected dimness indicates that these supernovae are farther away than they should be, suggesting that the universe's expansion has been accelerating for the past 5 to 6 billion years. The careful analysis of supernova data involves several critical steps: precise measurement of supernova light curves, correction for dust extinction and other systematic effects, calculation of distance moduli and redshifts, statistical analysis of large supernova samples, cosmic microwave background radiation. The cosmic microwave background (CMB) radiation, often called the afterglow of the Big Bang, provides crucial supporting evidence for dark energy. The detailed pattern of temperature fluctuations in the CMB reveals information about the universe's geometry and energy content. The most recent measurements from missions like the Planck satellite show that the universe is remarkably flat, requiring a total energy density very close to the critical density. The pattern of CMB fluctuations is consistent with a universe containing about 68% dark energy. The angular scale of these fluctuations matches predictions from models including dark energy. Large-scale structure. The distribution of galaxies and galaxy clusters throughout space provides another independent line of evidence for dark energy. Astronomers have conducted extensive surveys mapping the positions of millions of galaxies, revealing a cosmic web of structure that bears the imprint of dark energy's influence. Key observations include baryon acoustic oscillations. These standard ruler measurements show how the clustering of galaxies has evolved over cosmic time. The abundance and distribution of galaxy clusters, which is sensitive to the universe's expansion history. The growth rate of cosmic structure, which is slower than expected in a universe dominated by matter alone. Gravitational lensing. The bending of light by massive objects, known as gravitational lensing, offers yet another way to probe dark energy. Both strong lensing, where massive galaxy clusters create multiple images of background galaxies, and weak lensing, subtle distortions in the shapes of distant galaxies, provide information about the distribution of matter and the geometry of space. Recent surveys have used weak lensing to map the distribution of dark matter across large regions of space, measure how cosmic structure has grown over time, test whether dark energy's properties vary with time or location, age and structure of the universe. The existence of dark energy helps resolve several potential contradictions in cosmology. The age problem. Without dark energy, the universe would appear younger than its oldest stars. The flatness problem. Dark energy helps explain why space appears so close to geometrically flat. The structure formation problem. The observed pattern. Clustering matches predictions from models including dark energy cross-correlation of evidence. What makes the case for dark energy particularly compelling is the convergence of evidence from these different observational techniques. Each method has its own systematic uncertainties and potential biases, but they all point to the same conclusion. Roughly 2/3 of the universe's energy content consists of something that behaves like dark energy. Recent precision measurements have allowed astronomers to cross-correlate different types of observations, providing even stronger constraints on dark energy's properties. These include combined analysis of CMB and BAO data, joint studies of weak lensing and galaxy clustering, integration of supernova data with other cosmic distance measurements. Part 3. Theoretical understanding of dark energy. The theoretical understanding of dark energy represents one of the most challenging frontiers in modern physics, where quantum mechanics meets general relativity, and our conventional understanding of physical laws is pushed to its limits. The cosmological constant interpretation. The simplest theoretical explanation for dark energy is that it represents a fundamental property of space itself, a modern version of Einstein's cosmological constant. In this framework, every cubic centimeter of empty space contains a fixed amount of energy. This energy density remains constant as the universe expands. The associated negative pressure causes space to expand at an accelerating rate. The measured value corresponds to approximately 10 to the negative 29 grams per cubic centimeter. However, this seemingly straightforward interpretation faces a severe theoretical challenge known as the cosmological constant problem. Quantum field theory predicts a vacuum energy density that is roughly 10 to the power of 120 times larger than the observed value of dark energy. This discrepancy represents the largest disagreement between theoretical prediction and observation in all of physics. Quantum vacuum energy. The quantum vacuum, far from being empty, is thought to be filled with virtual particles constantly popping in and out of existence. Theoretical considerations suggest that virtual particle-antiparticle pairs briefly appear and annihilate. These quantum fluctuations should contribute to the energy density of space. The zero-point energy of quantum fields should generate a huge cosmological constant. Some unknown mechanism must suppress most of this vacuum energy. Various theoretical approaches have been proposed to resolve this conflict. Supersymmetry. A symmetry between fermions and bosons might cancel most vacuum contributions. String theory. Extra dimensions might dilute the effective vacuum energy. Quantum gravity. A full theory of quantum gravity might explain the small observed value. Dynamic dark energy models. Alternative to the cosmological constant are models where dark energy varies with time. The most prominent of these is quintessence. A scalar field pervades all of space. The field's energy density can vary both in time and space. Its evolution is governed by a potential energy function. Different potential functions predict different behaviors for dark energy. Advantages of quintessence models include potentially explaining why dark energy became dominant recently in cosmic history, allowing for interaction between dark energy and other cosmic components, providing a more natural explanation for the observed energy density. Modified gravity theories. Some theorists propose that dark energy might not be a new form of energy at all, but rather a modification of gravity itself. FR gravity generalizes Einstein's equations with additional curvature terms. DGP gravity proposes that gravity leaks into extra dimensions. TeVes, a relativistic version of modified Newtonian dynamics, MOND. These theories must reproduce the success of general relativity in the solar system, explain cosmic acceleration on large scales, pass increasingly precise observational tests. The anthropic perspective. The anthropic principle offers a different approach to understanding dark energy. Our universe might be one of many in a vast multiverse. Different regions might have different values of dark energy. Only regions with values suitable for life can contain observers. This might explain why we observe such a peculiarly small value. Theoretical challenges. Several fundamental questions remain unanswered. The coincidence problem. Why is the density of dark energy similar to matter density now? Why did cosmic acceleration begin relatively recently? Is this timing purely coincidental or physically significant? The fine-tuning problem. Why is dark energy so precisely tuned to allow structure formation? How can such a small but non-zero value be natural? What mechanism sets this value? Quantum classical discord. How does dark energy relate to quantum vacuum energy? Can quantum field theory and gravity be reconciled? What role might quantum gravity? Current theoretical developments. Recent theoretical work has explored several promising directions. Holographic dark energy connects dark energy to the holographic principle from string theory. Interacting dark energy models where dark energy interacts with dark matter. Emergent gravity suggests gravity and dark energy emerge from more fundamental phenomena. String theory landscape provides a framework for understanding multiple vacuum states. Part 4. Properties and characteristics of dark energy. Understanding the properties and characteristics of dark energy is crucial for unraveling its nature and its role in cosmic evolution. While many aspects remain mysterious, observations and theoretical work have established several key features. Fundamental properties. Energy density remains nearly constant as space expands. Current value, approximately 6.9 times 10 to the power of minus 30 grams per cubic centimeter, comprises about 68% of the universe's total energy content, becomes more dominant as the universe expands. Equation of state, characterized by the parameter W equals P over rho. P represents pressure. Rho represents energy density. Current measurements indicate W approximately equals -1 plus or minus 0.1. Negative pressure is crucial for causing acceleration. Distribution appears to be uniformly distributed throughout space. No evidence of clustering or local variations. Maintains constant density while matter dilutes with expansion. Permeates even the emptiest regions of space. Dynamic behavior time evolution may be constant, cosmological constant, or varying, quintessence. Current observations consistent with constant behavior. Possible slight variations within observational uncertainties. Became dominant roughly 5 billion years ago. Scale dependence. Effects most noticeable on cosmic scales. Negligible influence at galaxy or solar system scales. Becomes more important in future cosmic evolution. May vary with scale in some theoretical models. Interaction with matter and energy. Gravitational effects. Creates repulsive gravitational force on large scales. Effect increases with distance. Counteracts ordinary. Gravitational attraction. Doesn't cluster or form structures. Relationship with other cosmic components. No direct interaction with ordinary matter detected. Possible subtle interactions with dark matter proposed. Affects cosmic expansion rate. Influences formation of large-scale structure. Observable consequences. Cosmic expansion drives accelerating expansion. Rate of acceleration appears roughly constant. Effects visible in distant supernova observations. Influences light travel time across universe. Structure formation. Affects timing and rate of galaxy cluster formation. Influences cosmic web development. Impacts future evolution of cosmic structures. May determine ultimate fate of galaxies. Measurement challenges. Technical difficulties. Cannot be directly detected or measured. Must be inferred from cosmic expansion. Requires precise astronomical observations. Multiple independent methods needed for confirmation. Systematic uncertainties. Instrumental limitations. Atmospheric interference. Calibration challenges. Statistical analysis complexities. Unique characteristics. Negative pressure, most unusual and counterintuitive property, creates repulsive gravitational effect, violates strong energy condition, essential for cosmic acceleration. Scale invariance. Density remains constant despite expansion. Unique among known forms of energy. Implies special equation of state. Challenges conventional energy conservation. Theoretical constraints. Energy conditions. Violates strong energy condition. Satisfies weak energy condition. Implications for causality. Constraints from quantum field. Theory. Stability requirements. Must be stable against perturbations. Cannot lead to catastrophic phenomena. Must maintain coherent behavior. Should not violate other physical laws. Future evolution. Long-term behavior will become increasingly dominant. May lead to Big Rip or eternal expansion. Could change properties over time. May determine ultimate cosmic fate. Environmental effects. Impact on galaxy cluster evolution. Influence on intergalactic medium. Effect on cosmic structure. Consequences for astronomical observations. Observational signatures. Direct effects. Cosmic acceleration. Distance redshift relationship. Large-scale structure growth. Cosmic microwave background patterns. Indirect effects. Age of universe calculations. Galaxy cluster abundance. Weak gravitational lensing. Baryon acoustic. Oscillations. Part 5. Alternative theories and explanations. While dark energy is the most widely accepted explanation for cosmic acceleration, several alternative theories have been proposed. These alternatives attempt to explain the observational data without introducing a mysterious new form of energy. Modified gravity theories, FR. Gravity modifies Einstein's field equations, adds higher-order curvature terms, can produce acceleration without dark energy, must satisfy solar system constraints. Challenges include maintaining stability, avoiding ghosts, negative energy states, matching observational data at all scales. Brans-Dicke theory and scalar tensor theories. Introduces additional scalar field coupled to gravity. Allows gravitational constant to vary. Can explain acceleration through geometric effects. Modified versions still actively studied. Key features: variable gravitational coupling, additional degrees of freedom, natural extension of general relativity. DGP, Diwali Gabadadze Parati, proposes our universe as a 4D brain in 5D space. Gravity leaks into extra dimensions. Weakening of gravity leads to apparent acceleration. Problems include ghost instabilities, consistency with other observations, theoretical consistency issues, inhomogeneous cosmology, backreaction models, questions assumption of cosmic homogeneity, suggests apparent acceleration due to structure formation, based on averaging effects in Einstein's equations. Controversial but actively researched. Key aspects: nonlinear effects of structure, averaging procedures, scale-dependent behavior. Void models. Proposes Earth is near center of large cosmic void. Local underdensity mimics effects of acceleration. Challenges Copernican principle. Issues include required void size and shape, statistical unlikelihood, conflicts with other observations. Quantum gravity approaches causal dynamical triangulations. Attempts to quantize gravity directly. Suggests acceleration emerges from quantum effects. Based on discrete spacetime building blocks. Features: non-perturbative approach, emergence of classical spacetime, possible quantum origin of acceleration. Asymptotic safety, proposes gravity becomes scale invariant at high energies. Could explain acceleration through quantum effects. Active area of theoretical research. Implications: modified high-energy behavior, running coupling constants, natural emergence of cosmological constant, alternative matter theories, chameleon fields, scalar fields with density-dependent properties, adapt to local matter density, can explain acceleration while passing local tests. Properties: environment-dependent mass, screening mechanisms, local test compatibility. K-essence: modified scalar field theories, non-standard kinetic terms, can produce acceleration naturally. Features: dynamic behavior, sound speed variations, novel equation of state, emergent gravity, thermodynamic approaches, gravity as emergent phenomenon, acceleration from thermodynamic principles, based on holographic ideas, key concepts, entropy area relationships, information theory connections, emergence of space and time, entropic force theory, gravity as entropic force, acceleration from information gradients, novel conceptual framework, elements, information-based gravity, holographic principles, quantum information aspects, observational challenges to alternatives, consistency tests, must match multiple observational probes, need to explain all cosmic evolution phases, required to satisfy local gravity tests, challenges, matching diverse datasets, scale-dependent behavior, historical evolution, theoretical requirements, mathematical consistency, absence of pathologies, natural parameter values, issues, ghost-free conditions, stability requirements, energy conditions, future tests and prospects, upcoming observations, gravitational wave observations, improved cosmic surveys, higher precision measurements, potential, distinguishing between models, testing specific predictions, revealing new phenomena, theoretical development, refined calculations, new mathematical tools, computer simulations, goals, better predictions, model discrimination, understanding limitations. Part 6. Research methods and technology. The study of dark energy requires some of the most sophisticated observational tools and analytical methods in modern astronomy. This section explores the various technologies and techniques used to investigate cosmic acceleration and dark energy. Space-based observatories. Hubble Space Telescope, HST. Key capabilities: high-resolution imaging, precise photometry, wide spectral coverage. Contributions: supernova observations, galaxy cluster studies, deep field surveys, Planck satellite. Primary functions: CMB mapping, temperature fluctuation measurements, polarization studies. Achievements: precise dark energy density measurements, cosmic parameter constraints, large-scale structure insights. Euclid mission, launched 2023. Design goals: wide field imaging, spectroscopic measurements, dark energy specific mission. Expected outcomes: weak lensing surveys, galaxy clustering maps, dark energy equation of state. Ground-based observatories: Large Synoptic Survey Telescope, LSST. Capabilities: rapid sky scanning, deep imaging, time domain astronomy. Research focus: dark energy surveys, weak lensing studies, transient object detection, dark energy survey, DS. Instrumentation: 570 megapixel camera, wide field coverage, multi-band photometry. Scientific goals: galaxy cluster counting, weak lensing measurements, large-scale structure mapping, spectroscopic facilities. Major instruments: DESI, Dark Energy Spectroscopic Instrument. Foremost, PFS, Prime Focus Spectrograph. Capabilities: multi-object spectroscopy, redshift measurements, galaxy clustering studies. Observational techniques: supernova surveys methodology, systematic sky scanning, follow-up spectroscopy, light curve analysis. Key aspects: standard candle calibration, distance measurements, systematic error control, weak gravitational lensing. Technical requirements: high-resolution imaging, large galaxy samples, shape measurement algorithms. Analysis methods: statistical correlations, mass mapping, shear measurement, baryon acoustic oscillations. Observational needs: large galaxy surveys, precise redshift measurements, wide sky coverage. Analysis techniques: correlation functions, power spectrum analysis, statistical methods, data analysis methods, statistical techniques, key approaches, Bayesian analysis, Monte Carlo methods, machine learning, applications, parameter estimation, model selection, systematic error control, computer simulations, types, N-body simulations, hydrodynamical models, dark energy-specific codes, uses, structure formation studies, observable predictions, theory testing, data processing requirements, high-performance computing, advanced algorithms, data management systems, challenges, big data handling, real-time processing, data quality control, future technologies, next-generation facilities, planned observatories, giant Magellan telescope, 30-meter telescope, square kilometer array, expected capabilities, unprecedented sensitivity, higher resolution, broader wavelength coverage, advanced detectors, development areas, improved CCDs, quantum sensors, novel detector materials. Goals: better sensitivity, reduced noise, wider spectral range, computing advances, emerging technologies, quantum computing, AI/ML integration, cloud processing, applications, real-time analysis, pattern recognition, complex modeling, measurement challenges, systematic errors, sources, instrumental effects, atmospheric distortion, calibration issues, mitigation, cross-validation, multiple methods, advanced calibration, technical limitations, current constraints, detector technology, atmospheric effects, computing power, solutions, new materials, adaptive optics, algorithm improvements. Part 7. Implications for the universe's fate. The discovery of dark energy has dramatically altered our understanding of the universe's ultimate destiny. This section explores the various possible scenarios for the cosmic future, based on our current understanding of dark energy. The Big Rip scenario. Basic concept. Universe's expansion becomes infinitely fast. All structures eventually tear apart. Occurs if dark energy strengthens over time. Timing depends on dark energy properties. Destruction sequence. Galaxy clusters separate first. Individual galaxies break apart. Solar systems dissolve. Atoms potentially split. Timeline progression. Clusters, billions of years. Galaxies, millions of years. Planets, minutes. Atoms, final moments. Eternal expansion. Standard lambda CDM model. Constant dark energy density. Exponential expansion. Structures become increasingly isolated. Features: steady acceleration, no catastrophic ending, growing cosmic horizons. Long-term effects: galaxy isolation, star formation cessation, black hole dominance. Stages: local group binding, other galaxies disappear, universe becomes darker, information loss. The Big Freeze. Characteristics: gradual cooling, entropy increase, energy dilution. Timeline: star formation ends, matter breaks down, black holes evaporate, maximum entropy state. Physical processes: heat-death progression, matter transformation, energy distribution. Key phases: degenerate era, black hole era, dark era. Alternative scenarios: big bounce, universe contracts eventually, new Big Bang occurs, cyclic behavior possible. Requirements: dark energy weakening, quantum effects, modified gravity. Big Crunch expansion reverses universe collapses. Requires dark energy sign change, strong energy condition. Modified cosmology, timescales and transitions. Near future, next 100 billion years. Local group merger, galaxy isolation, star formation decline. Changes: visual sky darkening, structure evolution, temperature decrease. Intermediate future, 10 to the 5th power, black hole era, matter decay, information processing ends. Processes: proton decay, black hole evaporation, particle dissolution. Far future, beyond 10 to the 100 years, maximum entropy state. Quantum fluctuations, possible new phenomena. Characteristics: empty space, minimal energy density, quantum effects dominate. Observational implications, current evidence, acceleration measurements, structure formation, energy density evolution, data sources, supernova observations, CMB patterns, galaxy distributions, future observations, dark energy evolution, expansion rate changes, structure dissolution, monitoring, acceleratio, energy density variation, philosophical implications, cosmic meaning, ultimate fate questions, life's long-term prospects, information preservation, considerations, consciousness future, civilization survival, knowledge transmission, scientific understanding, limits of prediction, model uncertainties, theoretical constraints, issues, quantum effects, measurement limits, theoretical completeness, impact on life and intelligence, biological implications, resource availability, habitat isolation, adaptation requirements, challenges, energy access, material resources, communication limits, civilizational consequences, space colonization, energy management, information preservation, strategies, resource conservation, technology adaptation, knowledge preservation. Part 8. Current research and future directions. The field of dark energy research is rapidly evolving, with new projects, theoretical developments, and technological advances continuously emerging. This section explores the cutting-edge research and future directions in our quest to understand dark energy. Current major research initiatives. Dark Energy Spectroscopic Instrument, DESI. Primary objectives: 3D map of 35 million galaxies, precise measurement of cosmic expansion, dark energy equation of state. Technical capabilities: 5,000 fiber optic positioners, automated targeting system, high-precision spectroscopy, Vera C. Reuven Observatory, Legacy Survey of Space and Time, LSST, 10-year survey of southern sky, 37 billion stars and galaxies, time domain astronomy. Scientific goals: dark energy constraints, matter distribution mapping, gravitational lensing studies, ESA's Euclid mission, mission parameters, wide field imaging, near-infrared spectroscopy, 6-year operational lifetime, expected outcomes, dark energy distribution map, modified gravity tests, structure formation history, emerging research areas, machine learning applications, key developments, automated classification systems, pattern recognition in data, predictive modeling, applications, survey data analysis, systematic error reduction, theory testing, quantum gravity connections, research directions, quantum field theory in curved space, holographic principles, emergence of spacetime, theoretical advances, string theory implications, loop quantum cosmology, causal set theory, novel observational techniques, gravitational wave astronomy, standard siren measurements, binary merger analysis, cosmic expansion probes, multi-messenger astronomy, combined observations, cross-correlation studies, complementary datasets, future technology development, next-generation detectors, improvements, higher sensitivity, broader wavelength coverage, better energy resolution. Applications: precise redshift measurements, weak lensing studies, galaxy cluster surveys, computing, advances infrastructure development, quantum computing applications, AI, ML integration, cloud-based analysis, capabilities, real-time data processing, complex simulation models, large dataset handling, space-based instruments, planned missions, next-generation telescopes, specialized dark energy satellites, multi-wavelength observatories, technical advances, improved detectors, better calibration, longer operational lifetimes, theoretical frontiers, modified gravity, research, new approaches, non-local modifications, emergent gravity, quantum gravity effects, testing methods, observational constraints, numerical simulations, laboratory experiments, alternative theories, development areas, quantum vacuum models, interacting dark cis, validation strategies, observational tests, theoretical consistency, computer modeling, fundamental physics connections, research directions, quantum field theory, string theory, loop quantum gravity, integration efforts, unified theories, scale connections, consistency requirements, collaborative initiatives, international projects, major collaborations, multi-country observatories, data sharing networks, joint research programs, benefits, resource sharing, expertise combination, faster progress, cross-disciplinary research, fields involved, particle physics, quantum mechanics, information theory, synergies, new perspectives, combined methods, innovative solutions, future challenges, technical obstacles, key issues, systematic error control, calibration accuracy, data quality, solutions, advanced technology, better methods, improved analysis, theoretical challenges, outstanding questions, nature of dark energy, quantum classical interface, cosmic coincidence, research need. Part 9. Philosophical and scientific impact, the deep implications of dark energy. The discovery and ongoing study of dark energy have profoundly impacted both scientific thinking and philosophical perspectives about the universe. This comprehensive section explores these far-reaching implications. Scientific paradigm shifts, fundamental physics revolution, challenge to established theories, questions about general relativity, quantum mechanics implications, need for new physical laws, impact on basic assumptions, nature of empty space, energy conservation, gravitational theory, methodological changes, multi-scale approaches, interdisciplinary integration, new experimental paradigms, cosmological understanding, revision of cosmic models, universe's age and fate, structure formation, evolution timeline, observational implications, multiple probe requirements, scale-dependent phenomena, statistical interpretation, theoretical frameworks, modified gravity theories, quantum cosmology, multiverse concepts, philosophical implications, metaphysical questions, nature of reality, substance of space, time's arrow, causality concepts, existence considerations, something from nothing, vacuum energy, ultimate origins, fundamental issues, reality of mathematics, physical laws nature, determinism versus randomness, epistemological challenges, limits of knowledge, observable universe boundaries, measurement limitations, theoretical constraints, theoretical methodology, role of observation, theory validation, evidence standards, knowledge acquisition, instrumental dependence, mathematical modeling, inferential reasoning, impact on scientific practice, research methodology, experimental approaches, multi-messenger astronomy, cross-validation requirements, statistical sophistication, theoretical development, mathematical formalism, computer modeling, predictive power, data handling, big data analytics, machine learning, error analysis, interdisciplinary integration, field connections, particle physics, quantum mechanics, information theory, collaborative requirements, international cooperation, cross-field expertise, technology sharing, methodological fusion, combined techniques, shared tools, unified approaches, cultural and societal impact, public understanding, science communication, conceptual challenges, visualization needs, public engagement, educational implications, curriculum updates, teaching methods, resource development, media representation, popular science, documentary coverage, scientific journalism, technological innovation, instrumental development, detection methods, information preservation, historical context and future perspective, historical development, scientific revolution, paradigm shifts, theoretical evolution, observational advances, philosophical impact, worldview changes, methodological developments, conceptual frameworks, cultural influence, public understanding, technological progress, educational effects, future considerations, research trajectory, technical advances, theoretical development, observational capabilities, philosophical questions, ultimate understanding, knowledge limits, reality nature, societal implications, technology transfer, educational needs, public engagement. Part 10, Conclusion and Future Questions, a comprehensive analysis. This final section provides an extensive examination of the current state of dark energy research, remaining challenges, and future directions while synthesizing the key insights from previous sections. Fundamental outstanding questions: the nature of dark energy, physical essence, quantum vacuum energy relationship, scalar field possibilities, geometric interpretations, alternative theoretical frameworks, dynamical properties, time evolution patterns, spatial variations, interaction mechanisms, scale dependence, observational challenges, detection methods, measurement precision, systematic errors, instrumental limitations, the cosmological constant problem, theoretical aspects, quantum field predictions, vacuum energy calculations, renormalization issues, scale hierarchy, proposed solutions, supersymmetry approaches, string theory insights, quantum gravity implications, modified field theories, mathematical frameworks, regularization methods, effective field theories, non-perturbative approaches, holographic principles, the coincidence problem, temporal aspects, current epoch significance, historical evolution, future implications, timescales, anthropic considerations, observer selection effects, multiverse implications, life-supporting conditions, probability calculations, dynamical solutions, tracking mechanisms, coupled models, environmental effects, emergent phenomena, technical and observational challenges, measurement precision, instrumental requirements, detector sensitivity, calibration accuracy, systematic error control, long-term stability, data analysis, statistical methods, error propagation, cross-correlation techniques, machine learning applications, validation procedures, independent confirmation, cross-checking methods, consensus, theoretical framework development, model building, mathematical consistency, physical plausibility, observational compatibility, predictive power, testing methodologies, experimental design, statistical frameworks, simulation techniques, validation protocols, integration challenges, theory unification, scale bridging, quantum classical interface, gravitational incorporation, future research directions, observational programs, next-generation facilities, space-based telescopes, ground observatories, multi-messenger instruments, specialized detectors, survey strategies, sky coverage, depth versus breadth, time domain aspects, multi-wavelength approach, data management, processing pipelines, storage solutions, analysis tools, distribution methods, theoretical developments, new frameworks, modified gravity theories, quantum approaches, unified models, alternative paradigms, computational methods, simulation techniques, numerical algorithms, machine learning integration, quantum C, validation strategies, observational tests, consistency checks, cross-validation methods, statistical frameworks, implications for fundamental physics, quantum gravity connection, theoretical aspects, vacuum energy, quantum fluctuations, space-time emergence, information preservation, experimental approaches, high-energy tests, gravitational waves, quantum experiments, cosmological probes, conceptual challenges, unity of physics, nature of time, causality, information paradoxes, particle physics interface, standard model connections, Higgs field, neutrino physics, dark matter relationship, new particles, energy scales, hierarchy problem, unification schemes, symmetry breaking, phase transitions, experimental implications, accelerator searches, cosmic rays studies, underground experiments, space-based tests. Philosophical and methodological considerations, scientific methodology, epistemological aspects, knowledge limitations, measurement theory, theory validation, evidence standards, research strategies, multi-probe approach, cross-disciplinary integration, theory development, experimental design, future directions, new paradigms, alternative frameworks, methodological innovations, validation techniques, cosmological implications, universe evolution, initial states, current state, future scenarios, timescales, structure formation, galaxy evolution, cluster dynamics, large-scale structure, void development, ultimate fate, expansion scenarios, energy dominance, structure dissolution, information preservation. Thank you for watching. We hope you enjoyed today's video. If you did, don't forget to hit that like button and subscribe to our channel for more exciting content. Your support means the world to us. We can't wait to see you back here for our next adventure. If you have any feedback or ideas for future videos, drop them in the comments below. Until next time, take care and stay awesome. See you soon.